Hello everyone and welcome to Pi Gotham 2021. My name is Calvin Hendryx-Parker and I will be your guide today for deploying a Django virtual event platform using containers and Terraform. So we're really going to try and dive in and cover how we built our own platform for virtual events using cloud native tools. And so let's go ahead and kick this off. We're going to really start off though with the developer experience when it comes to getting ready for a cloud native deployment. Because if you don't start there, we're not going to be able to actually really fully accomplish a truly cloud native deployment experience. And I'll kind of describe a lot of the cloud native components as we go. But basically what we try to do is use all the tools we can from the platform we're in this case, AWS Cloud, to make our life a lot easier as developers and as for the DevOps experience, making sure it's a reliable platform, can scale to handle the traffic, and just generally makes it a much more enjoyable experience because I'm not having to deal with command line tools and monitoring servers. That part is handled by my cloud provider. So if we talk about the developer experience, let's dive in over here. And we're going to start off though with the developer's workstation. That's probably one of the most critical parts to getting this started correctly is that developer experience on their local workstation. If they can develop, and in this case, containers is the key here to being able to deploy these applications into a cloud native environment, we want to make sure that their experience developing locally is as close as possible to what we end up deploying into production. So to accomplish that, we use Docker and Docker Compose locally on the developer's workstations. And so that's where they start. And all of the needed services we try and mimic that are going to be in the cloud using Docker Compose. So for example, tools like Redis or Postgres, where we may have an equivalent cloud counterpart, such as the RDS in Amazon, which is a relational database service, or Elasticache for our Redis. We want the developers to be leveraging those same technologies, but doing it locally via containers. The goal being to get started onboarding as a new developer on this project, you can just clone the repository, either run the makefile command. We use makefiles to manage kind of local task running, to set up your container, to build your image, and then you do a make up or Docker Compose up, and you've got the whole stack running locally, making it easy for you to develop. And as part of that developer pipeline, we use whatever source control tool you would want. In our case, we're using Bitbucket for our source control management, and then we use the Bitbucket pipelines to then build each of those releases that are going to go into our sandbox, our dev, or to our production environments. That all happens inside of the developer's world, kind of where they have the most control. So from the makefile, they can actually kick off a Bitbucket pipeline to release to sandbox, which is like our staging or pre-production environment. And then their code commits trigger actions, events at the Bitbucket repository to kick off those releases automatically. So we have a continuous delivery and a continuous integration environment where it can run our tests and then deploy, if it's successful, into a sandbox environment that can then be QA'd. So that's the first step to our developer-friendly experience when developing on this specific platform. So we've got a container for the Django application. Then we also run supporting containers for things like the React app. So we can actually develop using the Express server for having nice debug tools. Another nice bit when using Docker Compose locally is like a lot of the IDEs support these containers. So for example, I'm using PyCharm. It makes it very easy for me to debug in a remote debugger running in a container that is controlled by Docker Compose. The next step beyond this is going to be how do we get our code released into production and into all the various moving parts that make up the infrastructure for our specific project. Well, if we go down here, this kind of starts off a little bit like, I guess, kind of a click salad. You may start building and sketching out some of the infrastructure using the AWS console, but no one likes clicking through a web UI, and no one likes completely building with the command line tools either for building out all of your tooling. So this is where Terraform comes in, and we leverage infrastructure as code using Terraform to model out the whole infrastructure for each of our environments. So that makes it easy to have the staging and testing environments match the production environment albeit maybe at a scaled back resource level, so it doesn't cost as much to run. That's all controlled from the Terraform standpoint. So we will sketch out what the environments will look like, sketch out even what the code pipeline environment will look like. That's all controlled with infrastructure as code. So if we zoom out on this project now, and I can show you a little more how that works. Everything in this AWS cloud box, and same thing for the deployment experience, is controlled by Terraform. No one modifies anything by hand or clicking through the AWS console anymore, because once you get to a point where you've got your Terraform files starting to flesh out what's really being built, it becomes much easier actually to modify the Terraform when changing some part of the infrastructure that you're using in production to deploy the application. So the key pieces here in the developer experience for the AWS cloud is going to be this whole code pipeline, code build, which is right now the Bitbucket pipeline produces the image, and that image gets shipped into ECR. So ECR is our Elastic Container Registry that stores where we will put our images for later use in our deployment environment. All of that's orchestrated by the code pipeline. And so once a new image lands in the ECR, the code pipeline picks up that event. So we're using all cloud native AWS here to listen for events such as images landing inside of a container registry. Code pipeline picks up that picks up the fact the image was deployed and calls some more tooling around code build to start running and producing the new versions of our containers that we'll be running, in our case, Fargate. So you'll see this icon right here is actually Fargate. We deploy into Fargate for our container hosting because it's a lot easier than running your own. So you kind of have a couple different choices between doing like Docker Compose, kind of roll your own, going for a full-blown Kubernetes service, which is kind of fraught with complexity. And if you don't need that level of complexity yet, you may not want to like venture into it. I feel like the Fargate gives us this right balance of managed services coming from the provider, in this case Amazon, and the power to run any image into a container that we want on the cloud. So the code build actually does a couple things when it comes to deploying our tasks. It sets up the initial tasks in Fargate for us, releases the specific version of the image for us. Then it also will run, for example, collect static to put our static assets into media storage. And also on the side, it will run and build our Webpack React application, so which gets deployed into a separate S3 bucket. So the React app is fully served out of S3. There's no Electron server or Express server used in that process at all. But that's all managed from the code pipeline and code build process. So as that gets released, we get a notification via a Lambda that's listening on CloudWatch for that to finish. And that goes into our Slack channel to let the QA team know that we have a new release ready for them to go out and look at on the sandbox environment. All right, next thing's next. We've got the developer experience down. Let's go over and talk about the application delivery. I'm going to have to zoom out a little more here because there's even more going on when it comes to how we deliver this application. I mentioned the application itself is deployed into a Fargate cluster. So you can see that right here with the Django specific application running. The application also has hooks. For example, we listen for specific channels inside of Slack, and that those Slack webhooks then get sent out to all the people who are logged into the virtual event platform using WebSockets. So we have a separate task running to manage the WebSockets inside of Fargate. We also have a separate task to set up to manage the celery workers that are in Fargate. And then to watch and monitor the celery workers, we have a set of a Flower instance running as well that is listening for errors or basically logging any kind of issues that we would see coming from the celery workers. What is interesting is you see 4 different clusters or 4 different tasks running here. The reason these are split up is because Django is just purely doing the API. So all of the React application is served and hosted off of S3 buckets. All of the access back into the Django application is purely via API calls or WebSockets. So we have the opportunity here to scale the API access differently than we would scale the WebSockets. There's different characteristics of those two workloads. WebSockets are going to be persistent connections that use a specific amount of memory for each one that's connected. So as more people connect to the application, we can spin up purely more WebSocket instances to handle those persistent connections, where we may not need to spin up more instances of Django to handle the API calls. And both of these are all sitting behind an application load balancer in Amazon, which that's sitting in the public subnet. And all of that also goes through CloudFront, which is a content distribution network. So CloudFront gives us 200 plus points of presence around the globe to deliver specifically the React application and any static media resources that are in the Django application itself, which is very handy because then that makes sure that everyone around the globe gets fast access to probably the most heavy resources that are in the application itself, which are these static resources over here. Then we also have the cellular workers back here. Those are doing common tasks like priming the cache for the Slack messages that are coming in. So once a minute or so, we actually will make sure the Redis queue has the latest versions of those messages in there. Also make sure that Redis queue has the latest schedule generated. One of the more load-intensive aspects of running the virtual event platform was generating the API responses for the schedule. It's shown in a couple different ways inside the application, and calling into Django and doing that many database calls was relatively expensive compared to other calls that were happening inside the app. So we pre-cache that schedule in Redis. So most calls for the schedule come right out of the Redis Elasticache. So it's very fast, very quick responsiveness to those kinds of calls. We also make sure we've got our Postgres database set up to use multi-AZ, so it's actually replicated across multiple availability zones inside of one Amazon region. So if you consider this to be one specific region, we'll have actually multiple subnets in multiple availability zones for high availability in case one of those zones were to go offline for some reason. The Django containers, the WebSocket containers, and Celery containers are all running across multiple availability zones automatically. And the automatic scaling that Fargate gives you pretty much handles that for you, which is nice because until you need to deal with that kind of complexity, you really should kind of push that over into the cloud provider's world and leverage those cloud native tools for you. Now, that's not all there is to the application. Specifically, we have lots of supporting services that are helping to monitor, helping with email delivery, the DNS things. Those are all actually shown over here. So Route 53, for example, we set up a wildcard domain that can serve any event.loudswarm.com. All the email hosting for the events goes through Amazon SES. All the monitoring is going into CloudWatch. So we have CloudWatch metrics and CloudWatch logs. So all the logging for containers. Another nice reason to use containers for this and not do virtual machines and just run this on VMs, kind of old school style, is that by default, the Fargate containers are going to just take the standard out logging from your Django application and ship them by kind of the standard way this would all work, would be shipping them over into CloudWatch. So all of your logs automatically get centralized into CloudWatch. All of your logs for the front-end access are actually being shipped into CloudWatch as well. It's nice to kind of centralize all that logging and just rely on the platform for this. Obviously, you have flexibility and you could be shipping these someplace else, but for simplicity's sake and being able to launch this quickly, leveraging these cloud-native pieces that are built into this platform was super convenient. We also have guard duty down here, so it's kind of a checkbox you turn on. You get some extra bits in there that are watching for malicious activity. The last piece is actually pretty critical to being able to deploy into multiple environments easily. This is the Service Manager SSM parameter store. The SSM parameter store is how we can store secrets for specific environments and only allow those environments to access their secrets. So for example, staging looks just like production. Staging is running the exact same images as production, but staging has different parameters for the database connection or for the Elasticache connection strings, or it can connect to specific services that are specific to the staging environment that are different than the production environment. Parameter store allows us to give through Terraform. Again, all this is set up with Terraform. We put into Terraform what specific environment variables we want to pass into that container on start, And then when those containers are started up, Fargate injects those environment variables coming straight out of the parameter store, which are also kept securely. So we can have things like database passwords in there, API keys and tokens. That's a great place to store those kinds of secrets so that they are not in plain text. They're not in some kind of source control someplace where they could possibly leak and expose secret areas of the environment. So the parameter store here is used to inject those into the environment as we are starting up those instances and launching Django to host the application. To coordinate all this, we still have, for example, a Bastion host down here. So you'll see these kind of shared management VPCs. So virtual private clouds, the VPCs, are ways to segment your account so you can control access between them. Certain things need to be global across multiple environments. So if this was the production environment, we'd have a VPC dedicated to production. We may have a VPC dedicated to sandbox. As this grew, you probably would want to have or not just a VPC, but a full account in Amazon dedicated to your sandbox environment, or a full account dedicated to your production environment to give it that proper level of sandboxing and isolation from one another. But having a management VPC allows us to put commonly accessed our global resources. For example, the ECR repository, this is where we store the images, needs to be accessible to all those various environments, and so that's why that's here. Having this public subnet with an EC2 Bastion host in there still gives us the ability now to access, for example, Postgres directly, so we can allow certain ports from that Bastion host to be accessed to Postgres. Or if we wanted to access, the new Fargate will allow you to exec into these containers. So if you wanted to actually get to a command line shell inside of those containers, that would be possible, but it's all going to be behind our private subnets and only accessible by a specific Bastion host, so that nothing inside this private subnet is exposed to the outside internet for obvious security reasons. I will recommend a couple other tools that are not Amazon specific, mainly Sentry. We used Sentry when we launched this application, and that was pretty critical to determining whether we were going to have performance issues or not. We did a lot of load testing as we went to go launch, and I'd recommend you do load testing as well. We used locust.io. It's a great Python load testing tool. We were actually able to write custom load tests for our WebSockets components of the application and for the normal API aspect of it. But during that initial load testing, Sentry actually helped us identify where certain components of the architecture were slowing down. It does more than just track errors and give you tracebacks for those specific errors, but the new Sentry features, like about 1.5 years old now, actually will do performance tracing. So you can actually turn on the performance mode. It will log some percentage of the requests with the full traceback to the performance. So you can actually watch, and this helps you determine where you've got your slowdowns or your hotspots inside your application. And that's where we found the schedule generation was actually one of our big hotspots, like a real slowdown. There were a lot of database calls that actually we eliminated some of the database calls, still wasn't fast enough, determined we really needed to cache a lot of that in Redis to make sure that the environment was stable and quick and responsive for some number of event attendees. With Locust, we were able to generate using actually Fargate. So we ran the Locust tests from another Fargate cluster. So we had plenty of compute, and we could actually scale them up to multiple containers to increase our availability of I/O for doing those kinds of tests, and then actually hit the application with Locust to simulate 500 users, 1,000 concurrent users, and tried to simulate real-world access. So logging in, browsing to specific sessions, starting to watch specific sessions, connecting to the WebSockets so we could see the amount of memory that each user would use as they connected to the WebSockets. We also have our conference messenger. So as the conference is going on, people can message through Slack. The site also uses a cellular worker that looks every so many minutes to see if there's an upcoming session to announce that into the various channels. So we had two-way communication with Slack, not only incoming webhooks, but also outgoing Slack messages using the API. And that was all done just with cellular workers, periodically looking at the data, understanding if there was a session coming up, and then sending those messages out. More recently, we've actually enhanced the platform and added in Discord support, which was different than Slack's messaging support, because Discord required a long-running WebSocket connection coming from Django. So we actually would spin up WebSocket instances that on start would initiate a connection using channels and the background workers feature of channels to talk to Discord and basically log into a channel, and we started receiving messages all asynchronously. Same thing, it's nice to be able to use the same images here as the Django image because we had all the ORM available to us, so we could actually start saving the messages off. As those messages came in, we can queue them and then start processing them asynchronously with our cellular workers. And maybe one thing I didn't mention here as well, there's just one image necessarily. We have a Django image, which has all the code for the Django piece, which also is what we would normally run your channels from. We're running the exact same image, but just as WebSockets for Fargate containers, so we can scale them differently based on the characteristics I mentioned earlier. Same thing goes for those cellular workers. This is the same image that is running the API, because it's going to have all the same code loaded. So really, we only have one Fargate image we are managing through the complete process. But what's nice, we can actually roll back. So if I click back over here, when we're looking at this developer experience and you wanted to, for example, rolling out new features, obviously goes through the code pipeline. But if you wanted to roll back to a specific tag, all the ECR images are tagged with which environment they're on, what version of that image is out there. And we also manage and collect the Git hashes on there as well. So if you knew a specific Git hash you wanted to roll back to, you can actually issue that command as a developer to CodePipeline to roll back to a specific version, and that would actually roll back all the images in the whole Fargate cluster, because they're all managed as one cluster. And then Fargate manages rolling those back for you. So the site stays live, and not until the new versions of images are rolled out does it actually start taking the old images out of the load balancer. So at any point in time, you may have 4 or 5 API Django instances, and that may double as it starts spinning up the new ones, and then the old ones will start draining off as the new ones start taking the traffic. So you get kind of that nice seamless release process without having to worry about downtime during that whole release process. Another nice feature to add into your applications is going to be a web application firewall. So up here, CloudFront can talk directly to the web application firewall. So before any malicious requests would even get down to your load balancer, that WAF can determine whether it's a SQL injection attack, or basically we just deploy the common like OAuth top 10. There's some really nice pre-built templates to start with, and then from there, based on your traffic patterns and what kind of attacks you may see in the wild, you can start tweaking your web application firewall to have additional rules, or you can even do there's some pretty creative things you can do with the WAF when it comes to like machine learning or logging and learning what kinds of requests are coming at your application. The WAF can do all that, but again, start with the basics, because if you don't, it gets overwhelming, and no one wants to be overwhelmed when they're deploying their event platform for all of your best friends to come and view your events. I hope you've all enjoyed this. Let me make sure I've not missed anything. I just think that this has been a great way to experiment with a lot of the cloud native technologies in kind of a greenfield way. A lot of times you get on projects and maybe it's legacy code. We were able to build this all from scratch in response to the pandemic in 2020. Because we needed a great place to host our events, and we wanted to build it in Django. So we were super excited to be able to host this all on the Django application server and all using cloud native tools. I want to thank you all for hanging out with me for this portion of PyGotham 2021. Again, my name is Calvin Hendryx-Parker. You can find me on the internet on Twitter as CalvinHP. You can also go to 6fup.com/blog and check out some of our blog posts. We typically write about a lot of these same kinds of topics out there. I want to thank the organizers and everyone involved, and I hope you all enjoy this show. Thanks.